Welcome back to my YouTube channel. Today we're going to be talking about the Fischer Esterification. The way I want to structure this video is first I want to introduce some of the key players involved with this reaction. Second, I want to talk about where this fits into the bigger picture of other ways to create esters from different reagents. Third, I want to talk about the general mechanism, so in other words, what the reagents are, what the products are. And then lastly, I want to talk about the specific mechanism, which has to do with all the details involved with how do we get from the reagent to the products. So first, let's talk about some of the key players. So right here, I've written at the top of this card 4 key players, or really 3. The ethanol is just an example of what some of the reagents could be. So if you look at the general mechanism, what you have right here is you have a carboxylic acid component and you have an alcohol component, which combine with acidic protons from hydrochloric acid or any other sort of acid to create an ester molecule. And the reason why I say component is because it doesn't necessarily have to be one specific thing for either the carboxylic acid or the alcohol. What difference between the different reagents that you could use in this is that the R group attached to the carboxylic acid, which right here you have written as R, could be anything, and for the alcohol, whatever is attached to it could also be anything else. And so lastly, I want to point out that the product of this is an ester. An ester is kind of just like a carboxylic acid minus the hydrogen, but it's also that oxygen that is for the hydroxy group is also bonded to something else. Otherwise, if all you had was just this carbonyl here, the carbon double bonded to the oxygen and an oxygen and nothing else on this right hand side, of course you have the R group, it would be a carboxylic ion and the oxygen would be negatively charged. But in this case with an ester, you have something bonded to the oxygen, therefore it's neutrally charged because it's bonded to 2 things as opposed to only 1. So let's talk about where this fits into the bigger picture. There are various other ways you can create this ester molecule using different reagents. And over here on this side of the card, I have written down 4 different possible ways you can go about it. In our video, we're actually talking about the 4th one. And the reason I have 1, 2, 3, 4 is because number 1 is the most effective way in which you could do this. In other words, it has the highest reactivity, the highest yield, that sort of thing. And then 2 and 3 and 4, this is the relative reactivity from 1 to 4. The first one, I don't know if you can tell because I have bad handwriting, but this is diethyl ether, Et2O, plus diazomethane, which is CH2N2, plus a carboxylic acid to get a ester. This is the most highly effective way. It has 100% yield. The only problem with this is that diazomethane is extremely explosive and dangerous. Second, you have acid chloride plus alcohol. Third, you have acid anhydride plus alcohol. And lastly, we have what we're doing today, which is a carboxylic acid component plus an alcohol component to create the ester. So that's the general mechanism. One more thing I want to note here. The reason why I have this little blue box, or rectangle rather, I guess, written here is because if you want to imagine the products of any Fischer esterification product reaction where you have the carboxylic acid component and alcohol component, you could simply, all you have to do is you have to align this part with this carboxylic acid part with the alcohol part, and all you really have to do is you just have to imagine that you're losing water and you combine at this point. So in other words, notice how you have these 2 hydroxyl groups, right? Here's one on the carboxyl and here's the alcohol. All you have to do is kind of just imagine that I'm losing this hydrogen, I'm losing this hydrogen, and I'm losing this oxygen. And whatever is left of the alcohol component is going to actually add to this oxygen to create this molecule. So, and you can, this is very simple. And so yeah, so let's talk about the specific mechanism. One of the things I also want to note before I do that actually is that this is a reversible reaction, meaning it can go to the products and the products can go back to the reactants. And so in order to kind of force it into the product side of it, what you'd actually want to do is you want to have an excess of the alcohol component. So I want to have many of the alcohol component. And part of the reason why for that is, as we're about to see, for every carboxylic acid component we have, we need 2 of the alcohols in order to make it work. And part of the reason for that is one of the alcohol components is going to add to the carboxylic acid at this point, and it's going to do so through deprotonation and protonation and so on and so forth. And the other component, what it's going to do is it's going to act as an acid or a base to cause the deprotonation or protonation. And one of the things I also want to mention finally before we go into the specific mechanism is that the HCl, the hydrochloric acid, is a catalyst in the sense that it interacts in the reaction, but it actually gets regenerated at the very end. And the same for the second, and the same goes for the second alcohol component. It also gets regenerates after having behaved as an intermediate and behaved in an acid base, doing this, that, and the other. One more thing. The specific reaction that I'm going to be talking about, or I guess the example, is for the carboxylic acid component. I'm going to have the most basic carboxylic acid you can have, which is simply acetic acid. So this R group right here is just a carbon and its hydrogens. And then for the alcohol group, we're going to have also the most basic alcohol you can have, which is methanol, meaning there's only one other alkyl group attached to it. Here you have two, which is ethanol. This and this. For our example, we're going to have a single alcohol group here and a single alcohol group there. So let's talk about the specific reaction. First, before I go into the details, I want to note kind of the direction that the reaction follows, because it's kind of messy the way I've written. If I had more space, like more paper and whatnot, it would probably all just be in one direction, but unfortunately I didn't, and it's kind of messy looking. So that's why I want to talk about first where kind of the steps, what direction the steps are going, because they do kind of like take different directions. So first, this is the first step, second, third, and then it goes down to here, and it goes left, and it goes down, and then it goes to the right. So it's a little confusing, sorry about that, but whatever. So the first step is protonation of the carbonyl oxygen of the carboxylic acid component, okay? And this is done by the hydrochloric acid. Now, one of the things I want to note is that there's two points at which there's two oxygens on this carboxylic acid. There's one here, there's one here. And because of that, the protonation can occur either here or here, and there's a reason why it actually only occurs on this oxygen, and the reason why is because if you draw the resonance structure of carboxylic acid, what you find is that this is the resonance structure, this is the other one, and it happens by moving the pi bond to the oxygen to create a formal negative charge, and making a pi bond here, creating a formal positive charge for that oxygen because it has three connections. The reason why the proton wants to go to specifically this oxygen as opposed to this one is because in this other resonance structure, the hydrogen is slightly positively charged and this oxygen is negatively charged, and so like different charges attract, so the negative is going to be attracted by the positive, whereas two positives are going to repel. Therefore, because the hydrogen is positively charged, slightly positively charged, it doesn't really want to go here because this oxygen is positively charged. It wants to go to the negatively charged one. And the way that we know that is by drawing the resonance structure of acetic acid. And again, acetic acid is just carboxylic acid, with the R group being a singular alkyl group. So yeah, and so this is why I have the arrows drawn to show that this oxygen is being protonated. The second part of it involves the actual, and the reason why we do this is we want to activate it towards the carboxylic acid. We want to activate it toward electrophilic addition of the alcohol group. So in this alcohol group, this oxygen is slightly negative, and then this carbon right here in the middle is slightly positive because there's a total net movement of electrons towards this oxygen because it wants it, because it's too positively charged. And so for that reason, again, like I said, this is the negative component. So this is, and then this is the positive component. This is the nucleophile in this case, and this is the electrophile. And so what's going to happen right here, this is reversible. You're going to add the alcohol component to the carboxylic acid component at this carbon point, and you're going to get this intermediate. It looks kind of messy. And so the problem with this is that our next goal in this really is to change this group right here. So this is a good leaving group and this is a bad leaving group relative to each other. And so for that reason, this is why it's reversible, because it could go back and this could leave. What we want to do next is we want to take another alcohol component to act as a base to remove this hydrogen here, in other words, to deprotonate this newly added alcohol component, such that it will now become such that we can transition from this being a good leaving group to a bad leaving group, and this to the opposite. And the way we get this to be a good leaving group, this hydroxy group right here, is by then afterwards using this protonated alcohol component to add the hydrogen that we just took from here to here. So really what we're doing is we're just doing a proton shift from this part to this part so that this becomes a good leaving group and this is the bad leaving group, to force the reaction to the product side. And so that's what I've written here. Here's the alcohol component. The other one, again, I said there's 2 for every 1 carboxylic acid, and this will be regenerated at the end, as you can see here. And all it's going to do is it's going to act as a base. It's going to remove this proton here, and then it's going to add it to this hydroxyl group, as you can see right here. I kind of had the arrows drawn backwards. That's my fault. But all you have to imagine is that this is the protonated. This is this after being protonated from this. And then it takes that hydrogen it just took and it puts it back over here such that this is water. And then it will, after this, it will expel, the water portion will be expelled, and there will be a pi bond to be formed in its place. And then from here, you're very close to the end, okay? This is very close to the actual ester part. As you can see, this is the oxygen, and this is the, whatever is attached to the alcohol group, okay? Which originally was this. The final step for at least the ester part is we're going to take another alcohol component now that this is a deprotonated alcohol component, so in other words, an original one, and we're going to deprotonate this hydroxy group right here, such that now there's no hydrogen there, therefore it is actually the final product, which is the ester. And so what I want to note here, this is kind of like the end of the reaction in the sense that now we have finally created the ester by combining these two with, in the presence of acid, in the presence of 2 alcohol components for every carboxylic acid component. But I want to talk about how we actually regenerate the original reagents, which is the hydrochloric acid in this sense and the alcohol component. Okay, so again, we're done here in the sense that this is the ester, which is what we wanted. And then now all we're doing is we're just regenerating the reagents. And the way we do this is that the protonated alcohol is going to react with the chloride ions, and it's basically just going to yank, the chloride ion is going to yank one of the hydrogens, which it really doesn't want to have, to the chloride, such that you now have the original alcohol component, you have the original hydrochloric acid, and then finally, what's most important is you have the original, or not the original, you have the ester. So yeah, just to summarize, you have a carboxylic acid component, you have an alcohol component. These two, through these steps of protonation, addition, deprotonation, protonation, removal of water, and then deprotonation, and then regeneration, those are all the different steps right here I just listed that we just talked about. What you get is the addition of the carboxylic acid to the alcohol component, such that you lose a hydrogen here, and an oxygen here. So whatever is left in between these 2 points combined, whatever that might be, whatever is here and whatever is here, they're going to combine. So that's it.